Okay, everybody. Hey, my name is John Stultz. I work on the Android systems team, and yet again, I'm going to talk about proxy execution. So people have been very kind and said that the answer to this question is no so far, but for me, it's a little bit. And so I do have a couple of topics. I definitely want to get into questions and that sort of thing through the talk. But if we don't get too rat-holed down sidetracks, I do have some non-proxy things to talk about too. So that's the teaser to try to stay awake through this. So previously, on the earlier episodes of the show, we've got a bunch of conference talks. The LPC, I'm going to kind of try to run through the overview of proxy pretty quickly here. But if you want more details on how the code works, I kind of did a deep dive on that LPC 2024 video. So that would be a good reference to kind of go and check out. So really quickly, just the why. So in Android, we have foreground and background tasks. We want to be able to keep the background tasks from affecting the foreground tasks. Using any sort of restraint or constraining tool, things like C groups or skid idle, those sorts of things, will quickly run into priority inversion, just a very classic problem when you have different priorities. And this is a big source of kind of UI jank that we run into because those background tasks that might be constrained, they're able to grab a lock right before they get rate limited in some way. And then we have to, basically all of the foreground tasks have to wait until that background task gets time to run again to release the locks. So with proxy execution, basically it is a generalized form of priority inheritance to solve a kernel mutex priority inversion. Basically those foreground tasks, when they're waiting for a lock, they're able to basically boost the lock holders by donating their CPU times. So those lock holders are able to run until they release the locks. And this basically allows us to be able to use, different ways of restricting those background tasks, be, skid idle, or, CPU or CPU shares or CPU set C groups. And it makes all of that functionality that is kind of unusable at this point usable. So as far as some of the benefits, this is a slide I've shown, I think, every year. And basically, we have a foreground task that's basically doing moving a file between directories. So it's just some file system operations. There's some background tasks doing the same thing, as well as a couple CPU spinners. If everything's unconstrained, you get to see, I don't know which one's that one. Okay, if everything's unconstrained, this is kind of the distribution and the latencies that we see. But if we do CPU share restricting of the background tasks, the average improves a bit, but we see this huge set of outliers. And these are actually crazy because this is a 15 microsecond average task, and these are 120 milliseconds. And so it really explodes when we have that CPU shares restricting the background tasks. With proxy execution, it basically gives us the behavior we want. We're able to drop the average down. We don't have all of those outliers. The background tasks are not interfering with the foreground tasks. It's just kind of what we want. So this is another example using a kind of more Android-focused approach. This is a calculator launch times. So we've got proxies in the red and vanillas in the blue. So this is basically just the baseline, running. These are the P90 latencies for running the calculator launch over and over. And so, with the baseline with nothing in the background, this is kind of where we are. If we add some CPU spinners in the background that are unconstrained, obviously we're sharing the scheduler, so you get larger times for that. If we use CPU share restricting of the background tasks, we get back down to kind of close order. If you see the variation here, these are P90s, so there's a lot of variance in the results. So I would kind of ignore it. It's a really rough scale is what you're looking at. So CPU shares are able to restrict the background tasks, for those CPU spinners. But if any of those CPU spinners call into the kernel, if they grab a lock, basically the launch times for the calculator just explodes. So it's not great. With proxy, we're able to solve this. So again, it's doing what we want. So some quick updates from last time. So we've made some good progress. So we've gotten some of the prep patches merged in 6.13. Lots of thank you to Peter for helping get this guided through. This basically added some reworking of basically moving the wake ups out of the wait lock context for the mutex lock. Had added some helper functions, and then most importantly, kind of added the notion of a split scheduler and execution context to the scheduler. I've also sent out 3 iterations of the same run queue proxying patches. And this basically adds the ability to do the proxying as long as the lock owner is on the same CPU as the waiter. And this basically has just got a handful of changes that's reworking the blocked on logics, doing that initial walk of the lock chain. And then basically, if we have any situation that's not on the same run queue, we just dequeue the donor just like the normal mutexes today. Gotten some good feedback on that from Peter, so I've been working on integrating those changes. Additionally, the V14 version of the patch was merged into the Android 16 6.12, and this is with the full set, so the full functionality. Unfortunately, it's disabled by default at this time because, as we talked about the vendor hooks in previous talks.
That's a nice moment to weed out all the vendor calls to start over, isn't it?
That would be nice if we could. So it's one of those things where we're going to give them a bit of time to transition. And so it's disabled by default at the moment, so the vendors can kind of go through and update their vendor hooks in order to have a concept of the split context. And, I've already gotten a few fixes from folks for edge cases where I had missed disabling the proxy execution paths. So that's been nice to get some feedback on. Here's just kind of an overview of the full patch series. I'm trying to kind of submit these in kind of digestible chunks that can be reviewed fairly easily. So we had the preparatory patches, so those have already been merged. This is the set that I'm currently kind of sending out to be reviewed. So this is the same run queue proxying. After that, there will be the proxy donor migration and return migration. So we're doing multiple run queues and cross run queues boosting. Then there's the sleeping owner and queuing and activation. This is basically handling the case where if the lock owner is sleeping, trying to take the tasks off the run queue and then re-adding them back to the run queue when the lock owner wakes up. And this is actually really complicated, so I've got a slide later on this, and then chain migration. And for V15, some of the highlights that we've got is, basically trying to address Peter's feedback for V14 was kind of what I did. I sent that out. Most of this is just splitting up some of the patches so they're a little easier to understand, and also reorganizing some of the changes that, were needed for later patches in the series that I'm not yet submitting, so kind of pulling that functionality out to be closer to where it's needed. Unfortunately, I found after submitting this to the list that there's some of those changes that I thought I could move later actually are needed earlier, and so I've got to kind of pull some of those back for V16. There's been a couple of little bugs that I've uncovered and had to chase down this week. As far as near-term to-dos, so one of the issues I have in the full patch stack is that I was running into the case where every once in a while I'd find that the lock owner, there's no lock owner for a mutex, but one of the waiters were still in this, the blocked on state was either in blocked or waking, which is kind of this intermediate state before we get back to running. So it seemed like we were missing some part of the wake up path that does the return migration where we make sure that we transition out of that. I have not yet narrowed this down completely. I do have a workaround in the patch series that basically, when we run into this case and find proxy tax, we're able to do kind of a manual return migration.
So the last time around when you posted this stuff, I got terribly confused on the BO block and BO waking thing, yep. And I suggested a number of approaches.
Yep. Yeah, so that's one of the things, I'll get to that in just a second if that's all right. So so this is something that I kind of want to make sure I understand where this bug is coming from, because this is just something that's kind of bothersome, but I do have a workaround. Another issue that I found recently is that with hot plug, I get a bunch of warnings. And this is actually, I found, coming from this workaround. So one of the issues is that manual return isn't checking to see if the CPU is still online. And so it ends up trying to return the task to the CPUs that aren't there. So that's, if I solve this, hopefully this won't be an issue anymore.
Can you go over maybe a little bit what is return migration?
Sure.
So you do unlock and then you return back to the CPU?
Yeah, so basically one of the issues we have is that in order to boost a task, we migrate the lock waiter to the run queue of the lock owner. And this allows us to run the lock owner on the CPU that they're able to run on. The lock waiter may not be able to run on that CPU due to affinity. And so we need to make sure that it comes back to a CPU that it can run on when the lock is released. And so we have to have this kind of step of making sure, and basically what we have is this BO waking guard, which is kind of this intermediate step. So there's this blocked on state structure that I have, or value that I have, that basically goes from runnable to blocked, and then has this extra waking state. And so when we do the wake up, where we say, okay, we need to run this, but we need to make sure that try to wake up evaluates and return migrates the task if necessary.
Do you have to do that for every lock release, or only when possible?
So this is something Peter brought up as well. So it's one of those things where initially I had it basically if the CPU, if the waiter was not able to run on the CPU it had migrated to, it would migrate back. There were some folks that I talked to who were concerned because on big little systems, you may have had the task moved to the proper CPU, and so it would have normally waiting for a mutex, its wake CPU would be on that big CPU, and so if it got migrated off to a little CPU, when the lock is released, you'd kind of expect it to come back on that big CPU, so it's not kind of messing up sort of the scheduler decisions by this boosting. So that. Is there something I need to do? Oh, okay.
In some cases, you can't even do it because you have to return it because of affinity, right?
Right. So sometimes there's a number of cases where you do have to, migrate back. Peter was commenting that it made sense possibly to just run it on the CPU it's on, assuming affinity allows, and that might allow the next task. If you have a long chain, you don't have to basically migrate the rest of the waiters on that chain back to the return migration CPU. It's something that I think needs to get a little bit of evaluation.
What about the calculations? So if this is, for real time, it's one thing, but for if you're doing deadline and you're running it like on the lock owner, mm-hmm. Now you basically the idea, I guess you're saying, you run it under the
donor's context.
Was that?
The donor's context.
The donor's context. Yeah. But if the donor's context is not been calculated for the CPU that the waiter is on, or the owner is on,
yeah.
How do you handle the calculations there?
That is still an open question. So
it seems you can feed that theory. We've been discussing with Luca and Tommaso, and essentially it's part of the design phase when you actually, you have to design your bandwidth to account for this. When using that properly.
Like anyone would be able to do that properly, but it's internal kernel ideas and not really understanding what might be shared. Because you'd have to know what the kernel shares.
Yeah.
You always would.
And I guess, yes, it's not ideal even when you use that, and there are also overhead to consider. You have essentially to overcome it a little bit, account for reality.
This was an issue that was brought up last year. And I guess talking to Yuri at Plumbers, he said, for now, let's put that one aside and we'll address that later. But if we do need to put in some restriction, we can have cases where you don't do the proxying for deadline tasks if we need to. So that was my kind of interim solution for a little while until Yuri suggested to just put that off for now. So Peter suggested a way to kind of avoid this blocked on state, which is basically instead of trying to have this guard to prevent it to be runnable, in that when we do the wake up, if it's a proxy task, we basically do the DQ first. And so that way we'd run through the normal try to wake up path. So this actually sounds pretty good. I really like this. The hard part is that in a number of the cases, in the places where we're deciding to do those wake ups, it is pretty deep in code that holds like the mutex wait lock. And so we have to get out of that context before we can grab the run queue to be able to do the DQ. And so it's one of those things where I've got to figure out some of the locking on that. So some spots are easier than others to do that. So that is something I'm looking at. There's another one that I was looking at because the blocked on state also kind of mirrors the task state in a lot of ways. I was trying to kind of split up the current enum, which is more of like a state machine, and instead break it up into flags. So we had the task being a BO locked would be a separate flag from the needs return. And then that needs return flag would only be set if we were proxy migrated, and then we'd have just kind of an extra check to do that.
I didn't really get that part. So, like, when you say DQ the block task, a block task is already DQ'd from.
No, that's one of the changes. I'm sorry, I didn't cover it this time. So one of the changes with proxy execution is that we keep block tasks on the run queue so that they're selectable, so we know what we want to boost.
Oh yeah, that okay.
So yeah, it's a subtlety, definitely. Yep.
And how is it continuing the run queue running state queue? So they are as a queue task, but not running a task?
Yeah, so
They are actually runnable, it's just that they run someone else.
Okay, so they are counting like delayed the queue task?
No, they're actually selectable. They are on run queue and runnable.
Okay.
Right. But though their task state may be like interruptible, right? So they're not a task runnable state necessarily.
Task that is traditionally blocked. Right. But we'll keep it on the run queue as if it is not blocked. And then once you select it, it will try and find someone else to run on its behalf, so that the tension goes away.
So the idea I was having with this approach might be that I could pull that, blocked on state into the task state. And that might avoid, I'm a little worried about races between the two state values because the task state is, a lot of write once sort of lockless operations on it. One thing I have kind of caution with this is that in the task state, there's a lot of cases where we just write whatever it is, we don't care what the value of it is, we just write runnable to it. And so in order to have this kind of check where we need to make sure that we say, oh, does this have needs returned before we actually make it runnable, is kind of the place where I need to figure out how to align that. All right. And other things that actually have come up near term since I've made these slides. Masami and Lance have some patches to add blocked on debugging for mutexes. Oh, okay. I mean, actually, it seems like it has very similar to some of the blocked on pointer stuff, and eventually,
it is somewhat similar, but for now.
Oh, okay. I was pulling.
By the way, I brought you in just to let you know. FY, I wasn't basically saying to use it or to have one use the other. I wanted you guys to be aware of each other.
Yeah.
So that when you do it, you're like not going to totally break one. That's just basically don't.
Well, it's because we're doing some stuff. It's just debug crap anyway.
Yeah. Well, the thing is a lot of it is very similar to what we need, and so I'm totally open to reworking my patches on top of their series. So that's something.
So Masami, just debug.
Okay.
It's useful debug crap.
Yeah.
Very useful.
So are there any drawbacks to going to the full TTW versus the previous approach? So it sounds like now you're going to do DQ and then the full thing, right?
So we still would do the try to wake up path, but what try to wake up would do is it would look for this BO waking state, and then it would do the DQ itself, and then continue on. And so Peter's idea is just shortcut that and do the DQ before you do the wake up, and that would hopefully simplify it. So that's a future thing, and then. I think that's all of the things I've got in my mind right now for my to-dos. Plans for the larger year, continue merging proxy execution upstream, trying to get those small digestible chunks kind of out to the list and reviewed. Also going to be focusing on supporting vendor experiments, getting them to move their vendor hooks over so that they're able to
So if
experiment.
you are talking to these vendors, ask them what the hell these hooks are for and whether or not we can get rid of them.
So the answer is probably going to be no from them at least.
Because they don't want to.
Yes, they see this.
Since they've got to invest effort anyway to support this, see if we can turn this effort around to get rid of it.
I very much would be in favor in fewer vendor hooks. I think the realities of it are often quite difficult. And when vendors see this as their value add that they want to, support and keep running and things that they've invested in.
Spell failure at, right?
Depends on how much they value priority inversion solution.
Yeah. A lot of the times they have their own priority inversion solutions in these vendor hooks. That's part of the reason why they're there. So the hope is that by having the proxy execution there, that they have less need for their vendor hooks. That's part of the reason why we're investing all this time into doing proxy execution. But it's one of those things where, So I'm going to try to support them going through that. This will be cases where people trying the full stack, shaking out any bugs as they kind of try to make it kind of really production ready. Also, I want to see about expanding to other lock types. I'm not sure kind of what I'm going to dive into exactly, but a lot of folks really want to see reader-writer SEMs have some sort of priority inversion solution because that's another source of priority inversion problems. Other folks want to see user space have access to this sort of benefit, so having it tied in through Futex would be nice. Also, replacing the RT mutexes would be nice. Though the one downside here is that the semantics for the lock handoff for RT mutexes are a little more strict. That can cause more overhead. We've seen in cases where switching a mutex from a normal mutex to a RT mutex causes us to go into the sleep path all the time instead of doing the optimistic spinning. And so I want to be kind of careful about, we may still have to have a conceptual separate between the proxy and RT mutexes, or the proxy mutexes and the proxy RT mutexes.
Futex thing, if you use the PI Futex interface, you can use this work.
Okay, with RT mutexes, right?
Yeah, I would just make it use regular mutexes.
Yeah.
That's an RT mutex name thing.
Yeah. So this is stuff that I'm going to be looking at this year. The other one too is that in expanding to other lock types, this is one of the things where the patches that Lance was sending that basically has that debug functionality for the blocked on. Lance's patch is already kind of multiplex multiple lock types behind that. So that was something I was considering to try to use for things as we expand to other lock types.
The problem with Futex, you don't know whether it's a lock even, and you don't even know who the owner is, right?
With PM Futex to do.
With PI Futex to do.
Yeah.
Does PI Futex already work with the proxy? Or?
No, because we ignore RT.
No, we ignore.
Yeah. So.
Okay, great.
So one of the topics I was going to cover, if people are interested, I didn't get to cover this at the LPC talk, is when we get to the point where if the lock owner is sleeping, one of the things is that if a waiter basically gets selected and wants to try to boost that lock owner, the problem is if not on a run queue, there's nothing you can do. There's no boosting you can do. So what do we do with that waiter that's been selected? In the proxy patches, basically what we do is we dequeue that from the run queue as well, and then we basically add it to a list on the sleeping task. And this allows us so that when that lock owner is woken up, we can also enqueue the waiter on the same run queue so that it can do the boosting. That's pretty simple, straightforward going through it. There's a couple of issues though. With one of the easiest solutions would be to say like, well, anytime you hit that sleeping owner case, always add yourself to like the root node of that, like the topmost sleeper. And then you can just have one list, and anytime that one wakes up, the whole chain basically would move as well. But one of the issues that there are is that with weight wound mutexes, you can have what I call kind of mid-chain wake-ups, because if there's a circular reference that's discovered in weight wound mutexes, the lock will be woken up with an e-deadlock. And so basically without the lock being handed over, the code will say, oh, this e-deadlock, it wakes up, it has to drop all of its locks and try to reacquire them again. And so this actually adds a lot of complexity to the code because, we basically have to maintain this tree structure, because anytime if we get a weight wound, wake up midway through the chain, we need to wake up that subtree and leave the rest alone. And so that means we still have to kind of maintain this whole tree structure. We can't just do one simple list. The other downside is that we can have these wake-ups happening in parallel all through this tree. And so basically you can have a situation where the sleeping owner might be woken up, but at the same time, multiple tasks inside of this tree might be getting e-deadlock wake-ups. And
you can at all times wake everybody up again and then start dequeuing again. It'll not be optimal.
Yeah.
It'll work.
Yes, that's
How
true.
often does this actually happen? I mean, if it's not a deadlock detection case, then it's basically a slow path, if you ask me.
Yeah, no, and this is that for most of proxy. That is the hope, is that all of this is fairly, only under heavy contention in the lock owners.
Well, it should
sleeping
be a
cases.
deadlock detection case if it's a few times, right?
Wait, when mutexes
You
are
have
used.
wake-up mutexes have the same issue.
Yeah.
They are
Well, no,
designed.
I'm saying they have this, but you should never trigger it in the kernel. That means it's a deadlock.
No, it does all the time.
Wake-up mutexes walk the chain until they hit the deadlock and then they back out.
Yeah,
Right.
and it's used very commonly in the DRM layer because they have big locking orders that they can't actually put a strict ordering to.
Oh, okay, so
And
they
so-
actually implement this.
Yeah,
They
and so
have- because they don't know how to do locking.
So, but we shouldn't be optimizing that weird case. I agree with Peter, just saying make it a simple list and then just rebuild the tree again when wake up happens.
yeah, I think it's just I'd be hesitant to have wake when mutex is down here waking up the whole structure.
But usually, I don't know, like I said, how much are they actually interacting with the whole structure? I mean, how many times?
That's true. Hopefully, we never have these these
So,
deeply distinct traits.
start simple, do the
Okay.
simple list, do the full wake up. If it becomes an issue, then we can then look at the more complex thing. Let's not create a complex solution for something that may only happen once in a blue moon.
Okay. I will try to evaluate that. I feel like there was the early version of this did have just a single list on the task, and I was running into a ton of bugs.
I remember having a single.
Yeah, and I had a ton of bugs around that, especially as soon as I started working with tests on the wait room mutex. So having this approach has been able to resolve those bugs, but looking at the code, it is messy. And one of the issues we have is that every time we do this wake up, this is a task struct, that's a task struct. So the locking between it, we have to always take the task PI lock, to do that. And so it's one of those things where you have to kind of like let go of all of the locking structures, do the wake up for one task, then move on to the next one. Initially, this was written in a recursive fashion, which is not great, but that was a lot easier to think about. I've reworked it to use a non-recursive approach, but that means that we have lots of lists to manage, and so it's definitely messier. So this is an area that when I get to this stage in review, I would love suggestions or ideas for other approaches.
Document the heck out of it.
Yeah, I keep on feeling like the file system folks have to have something that would be helpful for this sort of thing. But yeah. Yeah, and so one of the other problems I've seen with this as well, with the wait when mutexes, is that what they do is they basically, when they get their e-wake up or e-deadlock, they wake up, drop their locks, and then reacquire them right afterwards. And the idea is that hopefully in everybody dropping their locks and reacquiring them, some progress gets made. But that basically means I've seen in some of this code where we would be processing through the tree, trying to wake up everything on the subtree, and then the owner would come back before we were done. And so we could run into almost a live lock of constantly adding and removing things. So I've reworked it so we always do a finite amount of work on each wake up. And we only have a fixed list that we kind of pull off and process once at a time. So it's working, but it's again, this is kind of hairy space that I just wanted to have people thinking about.
Our team mutex does all.
Okay.
It's basically the same chain block that we have now.
Okay. So I should go look at that then.
So you can copy the code.
Okay.
And release the comments with the
Yes.
states. We spent an awful lot of time documenting all because it's more corner cases than actual state.
Yeah, it's just where you have like the big document with all the numbers, and then in the code you have number one, number two. I like that approach. So basically, you have this huge document. We're going to do this with 1, 2, 3, and then in the code you have it's labeled back
Yeah.
to the.
Okay.
And it labels back to, hey, this is error condition or exit condition number 5.
Okay.
And you have a matching code because I tried to do it, the comments in the code, but it got confusing very fast. So
Okay. Yeah.
I took this approach. But please,
I'll check that out.
if you attempt for your own mental health, start with documenting this right away.
Yeah.
I regret that I didn't do it when we wrote it in the first place. I reverse engineered it.
And then labeling the code with the comment. That's,
Yeah.
I do that now throughout the code.
Well, I'll give that a shot. So I appreciate the feedback on that. So I think that's it for the proxy side of it. I do want to say thank you to all the folks who have worked on this over the years. A lot of them in the room, Peter, Yuri, Valentin. And then also for the folks who helped review this, Stephen, Joel, I guess Pratik as well, thank you. And so, yeah, it's been fun getting to work on this, hopefully helping move this along. But so, with that maybe done, if anyone doesn't have any other proxy questions, I've got other things that are not proxy to talk about, which I'm really excited. Oh no, never mind.
Okay,
Go ahead.
I was just like, the same question, I guess, I asked every year on this topic is like Peter said, like, this stuff matters mostly when it's worth doing if you're having if your critical sections are long enough or short enough, is that? Because otherwise the overhead defeats the purpose of, because it depends on how long you have the PI, right? If your PIs are short, then all this overhead that we're adding will kind of
So the thing is, it all has to do with how much you're restricting the lock owners. Because they may only have it for just a nanosecond or whatever. But if in that nanosecond they get preempted, then it could be however long it takes for them to be able to be runnable again in the system. And so this basically avoids that and shortcuts it. So we say, hey, something that's important that we have selected to run needs this. And so we're going to donate that time so we can kind of get through. So it's one of those things where I don't know if, you could rework things to not use mutexes in the kernel, and that might be one approach. Spin locks don't have this problem because they're not preemptible. Yeah, well, that's true. That's true.
so you have smaller critical sections, it still makes sense to do it.
Yeah, because it's all about the potential for preemption, and then how long it's going to take for that task to become runnable again. And that's something that you can't. It depends on what else is going on the system at that time.
More than anything else, what you think about this determinism?
Yeah, so it's more like, to handle those few cases, we have to do all this migration and wake-ups and all that all the time, right?
Well, the thing is that those migrations only happen when they're needed.
Okay,
And so it's when an important task is blocked. And so it's one of those things. In all the other cases, we're still able to do optimistic spinning. The normal mutex handling. It's only when the owner is basically, not runnable at this moment. It's already gone off a CPU.
Something I didn't get. So in this last part, you just mentioned basically that in proxy execution you need to deal with also this, priority inheritance in a complete fashion for general mutexes, right? Not only RT mutexes.
So proxy execution provides that priority inheritance basically for normal mutexes.
So in this case, it's not a choice. It's not like in empty mutexes you have a flag, right, where the user theoretically can specify for user space. User can say, I want priority inheritance, or I don't need that.
So
assuming that there's a use case for that choice, but.
So no, I started this on mutex because one mutex is simple, and mutex is used all throughout the kernel. Ideally, when this all works and is there, then RT mutex simply becomes mutex. And the whole PI chain will misery just goes away. I mean,
It's real base.
This
Like real misery.
Yeah.
It just migrates.
Yeah. But
so yeah, I build it alongside the existing RT.
Okay.
That's gnarly code, and I didn't want to touch it.
Okay.
so For other topics, I do want to raise Kais's QoS API and ramp up multiplier series. I've been working with the Chrome team to try to integrate use of this, and it's shown some really nice results. So basically, using kind of a 2x multiplier and a 4x multiplier across a number of different benchmarks, we're seeing kind of really nice, 8 to almost 15% improvement over 612. So this is really looking attractive to folks. One of the things that's also very cool is that 612 is not a production kernel. So usually, the Pickle team will spend a whole bunch of time tuning and working on those vendor hooks to make sure that all of the heuristics and optimizations they can have for applications are there. But the cool part is with this QoS stuff on these benchmarks, this untuned 612 that doesn't have all of those optimizations was able to match the performance of the vendor, the production kernel. And so there's obviously like power management measurements I still need to do to kind of get the full picture of it. So I'm sure that there's some more sophisticated.
Is this multiplying thing that we had?
So yeah, this is Kais has patched to basically tweak the
it's not
ramp up.
I think it's a way to increase. So it's doing
It's a utilization.
It's tracking how long the task is running to make sure that it will reach frequency high enough to have a ramp up.
Especially for
stable across, starting from the little core or the big core, you ramp up frequency, or the ramp up of your compute capacity should remain the same. And this is a way to increase how fast you will ramp up your compute capacity that you will request.
But it's not the old power multiplier where we just swing.
No, it's not about it. It doesn't modify really the pure util average value. That's something beside.
Okay, so it's just faster up.
Yeah, and this is also per task, right? So that's the other nice part where it's not a global setting.
How many tasks did you set in for in the results?
So in Chrome, this is one of the things I don't know Chrome well enough. So it's basically, we've added it to a couple of task types. I don't know how many of those types there are. So I'd have to look at that. But it's one of those things where it seemed to have really nice behavior. So
the patch set itself contains a lot of stuff, right? You just
you
just took the ramp up multiplier with the quality of service interface for each task.
So that's something I still need to kind of try to thin out to have.
I think I already told you it would be nice to just extract this part and then we can discuss it, because I think there is a lot of infrastructure needed for this as well.
Yeah.
Like those there were two functions where you can transition from time, work log time, into how much utilization you will gain on a big CPU at the highest frequency. And this is what he's using for those little CPUs because they ramp up so slowly.
Yeah.
It would be nice to see how much infrastructure we have to get this functionality.
I took a little, after you mentioned that, I did take a little pass trying to see if I could pull out a couple of the patches. I only was able to pull out like one or two before I started running into infrastructure dependencies.
In this patch, there's also the old PELT multiplier, right? So it wasn't really clear to me. And there's also other functionality.
Yeah.
The margin stuff, right? He's using the same infrastructure. He's now having different margin for different CPUs, and it wasn't really clear to me which of these features essentially give you the better results.
So these results are using the whole stack that he has.
Okay.
And I am interested in trying to kind of filter that as we go. But
it's easier to digest when it comes to reviewing.
Yeah.
That stack hasn't been posted out now.
So it has been patched. It's submitted to LKML.
August last year.
Yeah. So Kais has been is under a huge workload as well as baking leave at the moment. So it's one of those things. I know he's wanted to have some time to iterate.
This is also related to the quality of service.
I'm working with them too.
Yeah, exactly. That's this patch.
Yeah. So. Anyway, I just wanted to kind of nudge folks if there's anything we can do to help move this forward upstream. If folks have ideas, I think that breaking it up is a good idea. And next time it goes on the list, it would be great to get some more review. Another topic. I don't know how much more time I've got.
10 minutes.
Okay. So proxy has taken a while. People have been interested in other approaches as well to try to solve some of the same needs. So there's been some work looking at putting apps in the freezer C group. People, I think, most of the time when they think of the freezer, they're thinking suspend and resume. Maybe they're thinking checkpoint and restore. But I think that's the extent of it. I don't know of anyone else who's using the freezer for much else. But the Android folks have been looking at, because the freezer freezes tasks outside of the kernel, so they can't hold any kernel resources. What if we just froze the background tasks? And so this would provide sort of a similar solution of being able to restrain those background tasks and avoid priority inversion.
Well, you still have the whole user space priority inversion problem. I mean, if there's a user log held, you freeze the task, someone's up for free.
Yeah, and so this has been another area that's been a problem, and so there's been side effects to this. So
this breaks queues and stuff like that. Sorry.
Oh, I'm sure. So so it would be, it depends on which task would be put in, I guess, right?
Yeah, but
So this is not usually for system tasks that go into the freezer. It's for other applications that they don't want.
Well, so the freezer doesn't distinguish.
Mm-hmm.
That's the problem. It's all or nothing.
Okay.
No, so the C group freezer is just the tasks that are in that C group.
In that C group, yeah, but still it doesn't distinguish between the tasks in that C group. They are all or nothing.
So if as an administrator, we put kernel threads in.
Well, kernel threads now, but then because it doesn't, the C group freezer only works on user space.
Okay.
But anyway, you can, if you have fuse or similar, then you can make mistakes.
Yeah, and then you get to keep the pieces.
Yeah.
So it's like, we can't stop user space from being stupid.
So
yeah, but you don't need to be stupid for this. It is like a mistake, because you may not realize that you're making a mistake. And that's
well, it's not. I mean, they say don't put system things. I mean, there's certain fuse that I guess would be something that you wouldn't want to put into a freezer.
Yes.
Yeah, true. But then, it very well may be background, and then you know.
It's like almost saying like all these guys are blocked on a big kernel lock or something like that. It's like a freezer is basically just saying these guys are like blocked on a lock. Like
it's outside of kernel space, which is nice.
No, what I'm saying is like a big kernel, like I shouldn't say big kernel, just a big lock. So it's basically telling user space, it's just like being blocked on all these things have to be texted and you release it. So if something depends on it, then it's like a deadlock.
Yeah, kind of generalizing the fuse case, it's like if anything in the kernel thread depends on user space, whatever the reason, it doesn't need to be a lock. It might be any dependency. Then you just deadlock.
And so we've already run into a couple issues with this. So binder IPCs to frozen tasks become problematic because the buffers that get sent to those frozen tasks can't get freed. And so they have to hang around until task wake
knows these tasks are targets and should then inhibit the
Yeah, and so there's already some patches to try to wake up those tasks when they need to do that. There's also being able to respond to synchronous requests has been problematic. But another thing that folks have mentioned is that, if there are recurring application timers, they build up over the time that the task is in the freezer. And then basically when they come out of the freezer, there's just this big latency when it's spinning, trying to address all those timers. This is very similar to a concern we had with suspend and resume in the early days. And this is why clock monotonic doesn't increase during suspend, because we didn't want to have, on every resume having to deal with however many ticks that we'd have to process coming out of that. So there's some folks who are interested in having some sort of a clock monotonic-like clock ID.
We have time namespaces now, right? So C group has its own time namespace.
Yes, but you can't, the time namespace is set up only, so you only set the monotonic offset when you set up the namespace.
Yeah.
And then it's read-only.
Yeah. And so
because that creates an insane amount of other problems if you make it movable during work time.
So people.
I mean, we could probably do something like some clock monotonic stupid or whatever.
Yeah. So basically, folks have kind of wanted something that's like the time that would be clock monotonic minus the task time in the freezer. So this would be a per task clock ID, which I'm not eager to have more of, but it would be. And the part that I'm most hesitant about is that it's not really clear to generalize what does this actually mean other than a solution to this problem, right? And so it's one of those things where I'd like it to have some kind of broader sense of what we're actually measuring with this time, other than, sort of like this monotonic minus the freezer time.
On the read outside, it's simpler. I mean, ignoring the totally broken semantics, but on the read outside, it's simple. But on the timer side, it's a total disaster.
Yeah, and that's where I'm just kind of hesitant. But anyway, I just wanted to kind of bring up that this is a thing that people are doing, so that folks can be aware and not, look too confused when it comes when something like this comes to the list. I don't know if this is going to be an approach. I'm trying to push for some other ideas, but just wanted to make people aware. Another thing that comes up often, I talk with folks who do real-time audio, and they are just constantly upset with the scheduler. Not so much really the scheduler, but more the DVFS responsiveness. This is an example. This is one of the things they run into is that this is not just audio playback. This is kind of dynamic audio generation. So the idea is that you have points where you're kind of either if you're like a synthesizer or maybe a game where you're kind of in real time generating new audio or mixing audio to create new sounds. And for this, their workload will change. So sometimes there'll be points where there's only 2 voices, and then all of a sudden you have 32 voices, and it's just a lot more work to generate. So in this case, this is a trace I've got from Android mainline on a Pixel 6. And basically, the workload's changed, so they've increased the number of voices. And so we start up here seeing underruns. And so this is kind of going negative as we move along. Now, the wild part is that this task, it's an RT task. It's been on CPU 7, which is one of the big CPUs. And so this should be ideal, placement-wise. But the CPU frequency just stays too low for this entire period of time. And this is about 100 milliseconds that's going across. The odd part is if you look really, really close there's another RT task that pops in and ended up bouncing that thread to another CPU. This was a higher priority RT task that just kind of came in for a little short period of time. And so it very briefly went to CPU 1, which is a little, and then ended up on CPU 5. The odd part is only after the task has come off the CPU do we see the frequency go up. And there's nothing actually.
There should be no DVFS.
Yes.
Well,
only in Android you have some load tracking RT. In mainline kernel we have a fixed OPP selection for running RT. What you're describing there is in the Android mainline kernel, not in the Linux mainline.
So that is Android. I didn't think we had anything on the RT side.
Maybe you should use Deadline instead of Python.
I know folks have actually did some research on using Deadline. Unfortunately, Deadline has not been something that folks managed to make work in Android, and there's unfortunately a strong negative feeling around it.
Well, I mean, it does need tie into the DVFS. It's not finished, but it has all the bits and bobs on to make it work.
Okay.
You just need to put some effort in.
Yeah. But yeah, the part that I was saying that this part looks odd because.
But I think there was some extra in Android for RT tasks. They don't go to max. They have some.
Yeah, that's what
exactly.
I'm saying.
Maybe this is set up wrong.
As soon as the RT task is runnable, we are selecting this system-wide CPU computer util-min value.
Okay, yeah. So
we don't have this for the RT.
Okay. But anyway, this part seemed odd because it's both on CPU 6 and 7 here. There is nothing running, and only seemed to do the ramp up after that. So it seemed like there's something on it. I need to go digging in
That's
there.
the wrong thing, because you just max out CPU for
But then, here it did finally on CPU5 ramp up. But they also see a lot of problems where on those migrations they see that it always starts at 0 again. And so whatever the utilization that was kind of figured out on the previous CPU, when they move to the next CPU, it doesn't seem
So it would be nice to get some of the feedback that was, I mean, as you say, better thought useful for this.
Yeah.
I personally didn't.
Okay.
But
I know Alessio had spent some time trying to do this, and it wasn't.
Yeah, but it would be nice to understand why they say it's not working. Because as Peter said, it's not finished, so maybe it's something is missing.
Yeah,
Most probably.
the other side of it is that it's gotten enough of a negative reaction from folks that it's hard now to even explore it. So it's one of those things where we can try to find some more details on that. But then lastly, I just want to say, everybody should try Perfetto. Perfetto is really like one of the coolest things that I've found since, joining Google. It's one of those things where very frequently you'll get something like this, just this image. And it's, a screenshot with some circles on it, and it kind of will demonstrate what a problem is. And that's all you get. And you're like, oh, yeah, okay. So it gives you a starting point to kind of go digging into a problem. Yeah, so it basically is able to digest traces from ftrace. It doesn't. Sometimes it can do normal trace files, but usually Perfetto will capture the raw trace buffers itself, so it doesn't say
reads the raw trace buffers, put it into protobuf, and then translate it. Also does perf as well. In fact, actually, I was just in London last week talking with Pimiano, who's the author.
Yeah. So Perfetto can't read some trace recording with the trace point, for example. Directly.
Yeah.
We're working on that.
Yeah.
That would be great.
Okay. So so basically the thing that I feel like is really valuable is that it becomes a very quick way to visualize issues, and it becomes a very easy shorthand between developers to talk about what the problem is. And I think this is something we could use in the community as kind of a common
You mentioned the frequency, CPU frequency signals. Are there other, what's the add-on functionality when you compare to kernel chart other than frequency?
So one of the things is that, yes, so the visualization is important for, the visualization is really important for just that shared language thing, but it's true kernel shark is a similar tool. The thing that I find that's really powerful about Perfetto is that it ingests that ftrace as a database. And so you're able to do queries against it. And so you may capture, a trace from 60 seconds and say, show me every time, and this is what this is actually showing. I basically said, show me every time we have an RT task that's, runnable, but not running for longer than a millisecond. And it was able to very quickly in this long time period isolate. I was able to put this debug track as one of those query results. And so I was able to see where on that debug track this was happening and zoom right in. And you could see, okay, well, this cyclic test was getting a cyclic test RT99 task, and it was basically delayed for 2 milliseconds because of network soft IRQ. And so it's one of those things where this is just really, really useful. The other cool thing it can do, this one sometimes it doesn't do as well because you can overflow the buffers really easily, but it can also do function graph tracing. And so it will be able to, if you want to scope it down, often you have to scope it down pretty low so that it doesn't get to be too much data so you don't overflow the buffers. But, it'll tell you what's going on. So here you can see the TCP code actually running where during this. I actually don't know SQL. I'm like the biggest SQL dummy. But I've been able to get enough little snippets of queries that I'm able to reuse and make it really efficient for me. There are other folks who do amazing things. Like they can be able to figure out what the run queue loads of each of the CPUs are based upon just the trace events. It's like they can just really cool.
The nice thing about it, because it's all JavaScript, you can use the Chrome inspector and put a breakpoint where it's about to do the query, and then just do whatever you want on the UI, and then you can monitor the queries. And one of the things I found is just to do that rendering, they use SQL to aggregate events, because when you zoom out, you don't need every event if it's a huge file. So they use SQL to aggregate a whole bunch of events for every line or whatever as a part of the whole image. So then that turns out to be fast because it's all running in browser.
Yeah. So the other thing is, Perfetto, a lot of the documentation is focused on Chrome OS and Android because that's kind of what it's most tightly developed with. But I've gone through and created a how-to on how to use it with just upstream kernels, so mainline kernels. You know, you can just do it on bare metal or QEMU or whatever. I really just want to get more people using this because I think it's such a useful tool for communicating. So that's the end of it. Thank you so much.
Thank you.